All right, so we're going to start talking about equations, and we're going to start with the simplest equations, and you're going to know a lot of this stuff already, but there's going to be some stuff that maybe you know about, but you haven't really formally defined at some point in your courses, or maybe you have it, but it's just been a while since you've done that. And, in addition to that, we're going to kind of introduce to you a concept about how whenever I'm asked to solve an equation, you can find the answer to that equation before you even start doing any work. Okay? And I want to show you that because I think that's important. Now, that's not something that you're going to be able to do on tests and quizzes. In regards to you'll be able to find the answers right away, but you're not going to be able to just write the answer down and get credit. Okay? You're going to have to show me the work and the processes that we're going through to solve this, because I want you to know how and why the solutions are what they are. Okay? So that being said, as we start going through here, and what this class is really about, this college algebra class, is this idea: is that we're gonna get a lot more proficient and a lot more skilled at the things that we kind of talked about last year in Algebra 1. Okay, and there's some new stuff as well that we're gonna be required to learn. But here's the reason we're doing this: when we get to a calculus class, okay, or any other math class beyond this, you're gonna see within like one assignment, like the first question might say, "Here's a linear equation. Do this work with it." Okay, and what I mean by that, there's two things in calculus that you do. You do it's called differentiation, and one's called integration. Differentiation's about finding what we call derivatives, which is simply just slope. Okay, integration is finding. We use what we call integrals to do that, but we're just finding area underneath a curve. Okay, on the xy axis. Those two principles or ideas are pretty easy, but what becomes hard is the algebra that's involved in those. Because in the first question, you might be differentiating something that is linear. The second one, you might differentiate something that's cubic. And the fourth one, you might do something that's exponential. And then the next equation might be logarithmic, and the next one might be trigonometric. Okay? So it jumps from, in one assignment, within maybe 5 or 6 problems, you might jump back and forth between 6 or 7 types of equations. And each time you get to a new problem, you have to kind of understand the aspects of that type of equation and how you deal with it. Does that make sense to everyone? So we're trying to get proficient at those, and that's what this course is set up to be. You know, at first, we'll start talking about like linear and quadratic equations. We'll spend a lot of time on those. And then we start talking about other polynomial equations like cubics and quartics and quintics. We spend quite a bit of time on those. Okay? And then we start talking about rational equations. Okay? Things that have fractions in them, and usually variables and denominators and stuff like that. And then when we see those, we'll go through the same exact kind of layout in regards to learning them and understanding them that we did with polynomial equations. And we'll go through that, and the next thing we'll come across is exponential equations. And then that 2 or 3 week span of time will be procedurally the same as what we did with rational equations, the same as what we did with polynomial, okay? But we'll be learning the different aspects of that type of equation. That kind of makes sense? So you're going to see this class kind of in 3 week, 4 week spans kind of like repeat itself in regards to procedures, but just with new types of equations. All right? So the first thing we'll talk about is solving linear equations. Okay? You guys remember what a linear equation is, what it looks like, what the defining characteristics are of it? Algebraically, what's the defining characteristic of a linear equation? Okay, great. Okay, so Fami's saying we're gonna go y equals mx plus b. That's fine. That's perfectly acceptable. I'm gonna write it this way. Okay, because right now I'm only gonna want to work with one variable. So instead of y, I'm just gonna put 0 in. Okay, and mx plus b is fine. Okay, I think the last class we used ax plus b. Okay, doesn't matter. But what the defining characteristic of a linear equation is that the leading degree, which means the highest exponent, the highest integer exponent is 1. Okay? Highest exponent is 1. And when we have, it's a polynomial, okay? It's kind of a bland or basic, most simplistic polynomial we have. But when you have a polynomial equation, if you have a degree here, then you have all the degrees that are less than that as well. All the integer, I don't say integer, all the natural number degrees that are less than that. So I've got x to the 0 as well here. Well, what is x to the 0? It's just 1. So we never really write it as x to the 0. And why I say this is in the next couple of days, we'll have x squared as the leading degree. So then I should have x to the first also showing up as a component to the equation. And I should have x to the 0 showing up as well, which is against the 1. When we're talking about cubics, we'll have x to the third as the leading degree. So then in that equation, I should have x squared, I should have x to the first, I should have x to the 0. Okay? Does that make sense? Or I at least should have placeholders for those terms. They might have coefficients of 0, so they vanish, but I should have those placeholders for each one of those terms. Okay? So that is kind of the generic linear equation format that we're going to go by. Okay? So anything of that form is linear, anything that is not of that form is not linear. Okay? You guys, when I asked what's the defining characteristic, a lot of you with your hands were tracing out a line, right? That's what you're getting. When you graph it, it's a line. Okay? So as we go through those 6 down there on the bottom, is this one linear? Okay? And the way we're going to define this or determine this is, can this be transformed into that? And absolutely it can. Okay? Is this one linear? Yep. What about this one? That one is not linear, okay? And the reason that one's not linear, you guys remember what the exponent is for square root of x? If I want to rewrite that? X to the, not negative 1, that's 1 over x. 1/2, okay? So whenever you're talking about roots, you're talking about fractional exponents, okay? And anything with a fractional exponent is never linear, okay? It's not, doesn't have that 1 there, so that's not. What about this one? Nope. What kind of equation is that? That's quadratic. Okay. So what kind of graph is that going to give you? What's that called? Parabola. Okay, so that's parabolic. What about this one? If I had like 3 over x to the first, let's rewrite that so I don't have a fraction anymore. How can I rewrite, going back to the laws of exponents, how can I write that so there's no fraction? Be 3x. Remember that exponent now? -1. Remember doing that? Okay. So is that characteristic there ever seen up here in the format? So that is not. Okay. That's referred to as a rational equation. You're going to have asymptotes and stuff like that, and curves, and we'll get to that about halfway through this class. What about this one? That one kind of looks like this one, doesn't it? Is this linear? It is, okay? Because the variable starts in the top already. So the way I can write this is actually 1/6 x to the first, if I prefer it that way, plus 1 equals 5. And then that 1/6 is just your coefficient for your linear term. Okay? So yes, that last one. Is that okay? All right, so we can identify linear. That's something we'll do every time we come across new types of equations. Just kind of differentiate: does this satisfy this type of equation or not? That recognition is pretty important. We come to the types of linear equations. Okay, and this is something you guys talked about in Algebra 1. We even talked about it in geometry quite a bit. You have 3 types. They're called conditional, identity, and contradiction. If you know what those words mean kind of in everyday vocabulary, you should maybe probably have a pretty good idea of how many solutions you're going to get here. Okay? Conditional means there's some requirement, right? Okay? You know, if I ask my parents if I can do something and they say, yeah, on this condition, that's a requirement that I have to pass before I can do what I'm asking to do. So 2x minus 1 equals 5. That is only true on the condition of what? What does x have to be for this to be true? Yeah. If x equals 3, then 2x minus 1 equals 5. You ever seen if-then statements in geometry? Okay, those were called conditional statements. And that thing is only true. Only a true conditional statement if x is 3. Okay? If x is 4, that's not true. If x is 10, that's not true. If x is any other number on the real number line, on a complex plane, that is not a true statement. Okay? So conditional with linear equations, you're going to have one solution. On identity, okay, does your identity ever change from today to tomorrow to the next day? So it's always the same, right? Whenever we see the word identity, we're thinking the same. When I look at 2x minus 6 equals 2x minus 3, now the operations look different here, okay, the way we've written it, but once I start doing a little bit of work, what do I recognize? The left-hand side is the right-hand side, correct? They're identical. Identity, they're the same. Okay? So what could x be here? Let me do this real quick. What if I added 6 to both sides? Add 6 to both sides to get that, right? So what happens if x is 10? What do I get? Get 20 equals 20, right? You get a true statement? What if x is negative 3? What do I get? Negative 6 equals negative 6, right? If x is a half, I get 1 equals 1. If x is 0, I get 0 equals 0. Is there ever an x value that you plug in, you not get an equal statement or a true statement? No. Okay? So that's an identity. And even if I go even a little bit further, subtract 2x from both sides, I get that. Hopefully you understand that 0 is always 0, right? This is always true. Always true. Basically meaning we have an infinite number of solutions. Okay? And identity, if you understand that concept, an identity is going to be very useful to us when we get to trigonometry. Okay? But because there's a series of equations in trigonometry that are always true, no matter what I use as an input value, that are going to allow us to make trigonometric equations a lot simpler for us to do some algebra with. Okay? That is always true. So we've got one solution, we've got infinite solutions. What's our only other option for the number of solutions we could have? None. Okay? And that's where a contradiction comes into play. And it's similar to this in regards to when I start multiplying stuff out. Okay, I subtract my 1/2 x's from both sides, and I get negative 1/2 equals 2. I get down to a statement that I have to kind of analyze. Is that ever true? No. Okay? That is a 100% false statement. So that gives me 0 solutions. Okay? Now, I want to kind of discuss and talk with you how this algebra we did by hand here relates to a graphical picture. Okay? Because this is something we'll go through every new set or new type of equation throughout the year. If I look at that first one, okay, you guys have done this with systems equations back in Algebra 1. Remember, the schools would give you like y equals 2x minus 1. You would graph that on a xy plane. And then you should give you y equals 5. You graph that on xy plane. And then you'd see where they cross, right? And you were looking for that point of intersection to be your solution for x and y. When I solve an equation, there is no y here, right? Okay, so I don't really care about what y is, but I can use the same approach. Okay, so I'm going to grab a calculator. Doesn't matter what type of calculator. I'll show you a couple different ones on how you can do this. But I'm just going to type in, I think it's y equals 2x minus 1. Type in that equation. I'm going to type in y equals 5, that equation. Okay? Now my solution to the equation, before I do any algebra, I know the answer to this is the x value of where those two things intersect. And that is 100% the case on all the types of equations we're going to go over in this course and in trigonometry. When you are solving an equation, take the left-hand side, make that a graph. Take the right-hand side, make that a graph. Go find where they cross each other. The x value of where they cross is the value that's going to satisfy that equation. Okay? Now I want to show you, because some of you could have done this. You know, some people do a little bit of work first, and maybe we deal with, maybe I added 1 to both sides first. So that would have left me with the left-hand side looking like y equals 2x, and the right-hand side looking like 6. Okay? Now you can't really see a huge difference here. We'll see another example later on that's a little bit more drastic. But this line here is y equals 2x minus 1. You see at the y-intercept is negative 1. This line here is y equals 2x. We have that y-intercept is 0, 0. So those are different lines, right? Does the line on the right, or the two lines in the yellow, still intersect at x value of 3? Absolutely. Okay? So as you manipulate your equations, though you change what the graph looks like and the things that it does, the solutions to the original equation, okay, are always represented as solutions into this manipulated equation. Okay? So you can kind of deal with that and hopefully understand that as we move on to more complex types of equations. We'll see that with quadratics, with exponential, with root equations, that kind of stuff, where the graphs change dramatically. Okay? Sometimes, like if we're doing a root equation, when we change the graphs, the changed algebra might produce a parabola, and that was never there at the beginning. Okay? But all the solutions to the green should always be in the group of solutions that are in the yellow. Okay? That's something to think about as we move on to other more difficult things. If we talk about, going back to, so those intersected one time, so those were conditional. If I go to y equals like 2x minus 6, and then I type in y equals 2x minus 3, I have two different lines here. Okay? See those two different lines, right? You see why we have infinite solutions? They coincide. They overlap each other. Every single x value that I choose will still give me a true statement. Okay? And then, what's the characteristic that we see with I'm not sure I'm going to type in the exact equation that PowerPoint had in, but something like that maybe. Okay? That would be a contradiction. Why is that a contradiction? Those two lines are what's going on? They're parallel. Okay? Now, as we move on to other things, other types of equations, I don't know, maybe you've seen this before, maybe in a science class. Have you guys ever seen that curve before? Okay? If I said, y equals sine x, and I say y equals like a half, so I'd be asking, my equation would like sine of x equals 1/2. You see a lot of intersections there, right? Okay, so that's a different type, there's an infinite number of solutions there. But what if I had this? What if I said y equals 3? Do those ever cross? No, so if I had that equation, sine of x equals 3, and I asked you what the solutions are, and you didn't know the algebra, but you went to the graph and said, well, they never cross. There are no solutions. So then maybe you could produce the algebra that convinces me of that. Okay? So I always like, when I'm doing maybe a problem that I'm struggling on or I'm confused about, find the answers first. If you had all the answers before you started doing the work, wouldn't that make the work a lot easier? So we have that ability. If you're on the ACT, guys, the ACT, probably about 50% of it you can do this way without having to do any work. Okay? Just grab your calculator and chugging along. Now, what stinks about that is the calculator that I use there is this one. Okay, so I'm going to show you something here. So in this course, guys, I'm not going to dictate to you what calculator you have to use. I'm going to try to show you an array of calculators that you can use that are going to benefit you, and you're going to have to decide, maybe I learn them all, maybe I learn one or two of them, and find your preference, okay? This one, I'm going to show you because you have to use it on the ACT, okay? And it'd be nice to be proficient at it. But it's the slowest of them. It's the most cumbersome of them because there's so many hidden features that we have to access through 5, 6, 7 steps. Okay? Where with Desmos or GeoGebra, it's extremely easy. Okay? So I'm going to go into, if I wanted to do that first equation. Okay? And actually I'm going to do, I think I had 2x plus 8 in there. So the equation I'm interested in finding the solution for, I'm losing my voice, 2x plus 8 equals 9x. Okay, if I wanted to find that, obviously you guys can do that work, right? It would be 8/7 would be x, okay? But if I go through and just say 2x plus 8 in y1, jump down to y2, and type in 9x, and then I hit graph. Okay, and this is the reason I want to show this. This is a pain in the butt because what happens in my graph? They don't what? Yeah, they don't cross. There's not enough screen there for me to see their intersection. So what I have to do is I have to go mess around with my window. Okay, which is maybe you guys mess around with the window and have to it all. Okay, it's kind of a trial and error thing. Okay. I'm going to take a look at what I've got right now. It looks like -3 to 3 on my x-axis, and I don't know, maybe -3 to like 10 or something like that on my y-axis. I need more y-axis values, right? So I'm going to increase that. So I go to my window, my y maximum, I don't know, maybe I go 10, and I see what happens. Go back to graph. Okay, and I'm kind of right on the edge there, right? So maybe I go back to window again. And I make it 13. And I hit graph. So it's a trial and error type thing. The more you mess around with it, the more you look at your initial graph and kind of think about how much more room do I need, to be allowing you to change that window a lot faster without going back and forth multiple times. But that's kind of a pain in the butt. Now, if I want to find the intersection of those two, I cannot just do this. I can't just take my cursor and start moving it because of the pixels. Okay? My answer is 8/7 is about 1.14 as a decimal. So that's close, right? But that's not the answer. So what I need to do is that there's built-in functions. I hit second and go up to this trace button, which takes me to calculator functions. Calculate functions. And I'm interested in where they intersect, right? Okay. Well, throughout the year, we'll use all those options. We'll intersect. And now it says first curve. Okay. And it says curve because you could have parabolas, cubes, that kind of stuff. And a line we can view as a curve. It's just not curvy. Okay. So I'm going to move my cursor to where I'm interested in the intersection, where I think the intersection is. And I hit enter. And then it's going to say, jump me to the other curve, the second curve. Go hit enter again, close to where I think they intersect. And it's going to ask me to guess. I don't know why it says guess, because it's going to find me the answer. 1.1428571. Okay? Now if I wanted an exact answer, that doesn't get me anywhere, right? So I probably can't take that and change to 8/7 very easily. Okay? But once I know that that is the answer and I go through the handwork and I get 8/7, I can take 8/7 on the calculator, divide it out, and see what I get, right? I can validate my solutions that way. So, hopefully you agree that that's a little bit more cumbersome than maybe taking this calculator here when I got 2x plus 8 typed in there, 9x, and now if I want to move around, I can just click and slide, no window, guessing there. And if I want the solution, all you gotta do is click on this, one of the curves. See that gray dot showed up? Is that x value 1.14? That's a lot quicker, isn't it? Okay. This is Desmos. You guys used Desmos last year? Okay. You just go to www.desmos.com and it's that calculator. It's a lot like Algebra, but it's a web interface. So it's just a website. You can download it too if you want to. All right, so let's get into some examples to help us get. What you're going to see is we're going to go through like a day, 2 days of just examples of these kind of, I don't want to say elementary, but more basic types of equations before we start getting into some more complex ones. I'm not going to do example 1 with you. Okay? If you can't do example 1, I think we've got problems with pressure in this class. Okay? I said do example 2. I think those are things that you should be proficient at. And do want to talk about example 3, not because you can't do it, but there's some things here that we need to talk about. In example 3, we've got x over 6 plus 2/3 equals 3/4x. Just something to remind yourself of as you are working with equations that have fractions in them. One, we should be able to do this without getting rid of them. Okay, because that's 6th, 7th grade work, okay, with fractions and adding fractions, subtracting, multiplying, dividing. But that is going to be time consuming. So the fastest thing to do is to change all of those through multiplication. And the way we're going to change them is to multiply by a what? A common denominator. Okay. Now I'm glad you said common denominator because it doesn't matter whether I multiply by 12. And when I say common denominator, I'm talking about a value that each one of these divides into a whole amount of times. Okay? So, for instance, all of those divide 12, all those divide into 12. If I said 18, is 18 a common denominator? No. 6 and 3 will divide into 18, right? A whole number of times. But 4 does not, so that's not a common denominator. Okay? Usually you're taught LCD, least common denominator, because that's going to make your coefficients when you create this new equation a little bit easier, but it doesn't have to be an LCD. If I'm not sure about what my common denominator is, take all your denominators. Any denominator shows up. Take 6 times 3, 18 times 4 gives me 72. If you multiply everything by 72, it will still work. It's just that your coefficients are going to be 6 times bigger than what they need to be. Okay? The way I do it is I find that LCD, and learning this with just real numbers right now makes it a lot easier to kind of connect the dots when we start multiplying by like variable expressions as LCDs. But I'm going to multiply by 12. So I'm going to take this thing here, multiply by 12. That thing there, multiply by 12. That thing there, multiply by 12. Okay? And when I'm multiplying by 12, I'm multiplying by 12 over 1. So it's a fraction. So I'm going to just show you this, how this works out and why we can do this in this first equation, or sorry, first ratio, and then kind of do it a little bit quicker for the other ones. So that's what this is really saying right here. Okay? So that gives me 12x over 6, right? But 12 is 2 times 6, isn't it? Over 6. Or we can do it this way. Maybe we can go even further. It's 2 times 2 times 3 over 2 times 3, isn't it? Okay? What happens with maybe this 2 over that 2? What is that a factor of? That's just 1, isn't it? 3 over 3 is just 1, right? So when we'll have just 2x, correct? Okay. That's why up here we can do this. It's a factor of 6 and that 12, they cancel out, leaves me with a 2. 2 then times that numerator is 2x. Here, there's a 12 and that 3, there's a factor of 3 inside 12, cancel out, gives me 4. So I multiply by 4 and I get 8. Same thing happens here, it's a factor of 4, both those. Leaves me with a factor of 3. 3 times 3 is 9. So we get that 9x. And that was the equation I was showing you with the calculator a moment ago. So this should get 8 sevenths as an answer there. Is that all right? Now, why I do it that way and why I set it up that way, and I think it's a good practice for you guys, is that eventually your denominators, your LCD might be something like this. And you got to multiply every one of these things by that. It'd be a good idea to write that here, write that here, write that here, and then start canceling out the factors that you cancel before you start multiplying. Okay, so throughout the year, not only will I show you, the steps and the logic, but maybe some convenient procedures that I have found students adapt to pretty well, and it usually benefits them. I'm not going to do example 4 is kind of a little bit more of a convoluted question than example 1 and 2 was. It's just a little bit more foiling. Foil just distributing. I think combining like terms, so let that one go. I think that one's important to talk about because there's multiple approaches here, but hopefully, as we talk about both approaches, you see that they're the same. What kind of equation do we call that when we have it back to geometry? A ratio equal to a ratio. One ratio equal to one ratio. Starts with a P. Proportion. Okay? And if you got proportions, what's the number one algebra technique that you like to use when you solve proportions? Cross multiply. Okay? Product of the means is equal to product of the extremes. So if I cross multiply, just be careful. And this is where people make the biggest mistake with this. Is that they'll go 3 times 2x hit 6x. And then the next thing they write down is minus 4. They forget that that's a quantity, so I got to distribute the 3 to both of those. So it's minus 12. And then when I cross multiply those two, 16x plus 12. Now, what I want you to realize is, hopefully you can do the rest of that equation. I'm not going to go any further with that. But there's another approach that we could use. Are those fractions? Can I multiply everything by an LCD? So if I multiply, I'm just going to rewrite this whole thing. 2x minus 4 over 4 equals 4x plus 3 over 3. If I'm going to multiply by the LCD, it's going to be 12, right? At 12 and that 4 will cancel, leave me what up here? 3. So when I multiply that 3 through this 2x minus 4, is that not the same as that right there, that product that we did when we first multiplied the extremes? Does that make sense? So you might be a person who says, I didn't do it that way. I didn't use cross products. I multiplied by an LCD. It's the same thing. Yes, you did. Okay? But you might think because the steps are a little bit varied that you're not doing the same thing, but you essentially are. Is that all right?
Pardon the interruption. Just a reminder, the senior class meeting will take place today during walkout time. All seniors should report to the auditorium. Sit as close to the front as possible. Again, senior meetings, class meeting in the auditorium during walkout time. Thank you.
All right, so we'll do this one. We'll start this one on Tuesday. But is that a proportion? No, because that says a sum of two ratios is equal to one ratio. That violates the definition of proportion. So is cross multiplying going to work here? No. And that's where a lot of people struggle because they think, well, that looks like a proportion, so I start cross multiplying, but they don't know what to start multiplying. They just randomly do stupid stuff. If I wanted to develop this into a proportion, I need to do that. I need to condense that. I need to do that algebra, make that one ratio. Then I can set that one ratio equal to 2/3 and now cross multiply. But I think that's more work than was necessary. That approach there, you're probably going to want to multiply everything by 30. That's the LCD, right? Get rid of all fractions, and now you have a linear equation. That's a linear equation there, but you have a more, a cleaner looking linear equation. Does that make sense? All right. On the other side, I put up an assignment 1.2. It doesn't have any equation stuff in it yet. It's just distance and midpoint. Right now I got to be due on Wednesday, but probably what I'll do is, as we move through this section and the next section, just keep adding questions to that and moving the due date back. But you don't want to get to the point where if I put 35 questions in that, you got one day to do those over 3 or 4 sections, okay? So start it. Right now I think there's like 16 questions in it. You should be able to do all of those. But be kind of time management wise, okay? Be intelligent about that because it will